Cool. All right. Hey everybody, welcome back to being on campus. Hope you're all glad to be here. Tonight we got Dani or Matthys giving a talk about LLVM and code analysis. So give him a warm welcome.
All right, welcome everyone. So today, basically, I'm going to cover some of the basic introductory stuff related to doing code analysis. If you want to analyze code, the basics you need to know from compilation, and then going over some tools and frameworks you can use to make your own analysis tools. So a little bit about me. So I am a recent graduate. I finished my Master's of Computer Science last semester, and I also have degrees in mathematics and IT. I'm also one of the tutors here at UQ. I've tutored 2010 and a few other courses. I also have my hobbies include swimming, programming, and long walks on the beach, which is always good. Okay, so before we get started, so I've made a repository available for anyone who wants to follow along. It contains some template code for building a code analyzer. So the reason I put this on before we get started is because The LLVM libraries, which this tool depends on, are quite large. It takes a while to download. It also takes quite a while to build the program because of all the LLVM dependencies you need for the things we're going to cover. So it does take about, I think I tested this out a bit earlier. It took me about 20 minutes to build the tool, to about 10 minutes to download things. So yes, hence we start this off beforehand. So you can just clone the repo. And in there's a setup script which you can run, which will download everything and get everything set up for you. There's also on the README for the repos, I'll go to here. You can see that, so you can either run the setup script, or if the setup script doesn't work for your machine, so I try to make it as machine agnostic as possible, so it will work on Mac or Unix systems. Those are the only ones that's supported, so it assumes you have apt or brew installed on those machines. So if the setup script doesn't work for you, you can follow along and just do the step-by-step installation. It does the same thing. The script just makes it, does it all in one line in case, and hopefully that works for most of you guys. But yes, so you can follow along using the secondary steps if the script should fail for some reason on your machine. Okay, but getting to the talk itself. Okay, so basically what I'm going to cover are the very basic knowledge for where to start off with when you want to analyze source code. So that includes looking at what abstract syntax trees are and control flow graphs. I'm not going to go into much depth into these sort of topics because the field is quite massive, so I'm just covering some of the introductory level things, because to delve into that, there are literally several university courses dedicated to this field, so I'm just going to skim over the basics to get you guys in the mindset for, and then so you guys are ready to understand what the code we're going to write later on will be doing. And then I'm also going to do some a basic introduction into what LLVM is, because that's the library the tool we're going to build uses by default, and just some introductions as to what the frameworks you'll be using there. And at the end, we'll go through a nice demo where I'll be showing you guys how to build a very basic source code analyzer program, which you can then extend or play around with in your own time. All right, so how do we represent programs? So whenever you've written a program, you would be writing source code, be it Python, C, JavaScript, Java, all those languages, you write some code. So that code has its own syntax, its own constructs, its own keywords, all of those the syntactic rules. And in general, these rules are known as a grammar. So every language, every programming language is based on some grammar, which is just the set of rules which say, okay, this language has these constructs, it has these keywords, it has functions, it has variables, it has structs depending on the language. It has these sets of constructs. And the grammar just basically says, okay, you're going to have these combinations of symbols, of letters, and those combinations are interpreted in some way, and they fit together in some way. So that's the general thing. A grammar is just this set of rules which says what this language looks like. And in general, of the grammars for programming languages you would have seen are quite massive. There's a lot of potential different keywords, a lot of combinations of things. So if you look at the grammar for a language, there's a lot of constructs. Even basic languages have quite a bit of grammar rules to follow. But yes, so all of the parsers, the things that compile your code and then run them, they understand these grammars, and they can convert this grammar into something known as an abstract syntax tree. So an abstract syntax tree is basically the logical representation of your code you've written, and that's how the computer can understand what your code is actually meaning. So it basically takes your source code, interprets it following some grammar rules, and creates a tree. So for example, this is a bit of C source code. It's a very small function. So it just adds two integers, returns an integer, and running this through the compiler, this is the sort of syntax tree you will find. So you can see what it did. It creates these constructs. So the grammar says these these combinations make these objects, and objects have, it's sort of the tree nature. For example, if you have the plus sign has the left side and the right side of the plus sign. They're the children of a node. So in this case, we can see this A and B, they became expressions. So a declaration reference expression, which just references a variable. So that A is a reference to a variable, B is a reference to a variable. They get cast to integers. This is how in this case the grammar says it happens. And both of the A and B are both children of a binary operator, and the binary operator is a plus. So you can see how these things sort of fit together. In a child, so a plus has two children, left and right, and then the binary operator is a child of the return statement. The return statement is a child of the curly braces, and the curly braces are one of the children of a function declaration, which is the add function. So the add function has two parameter declarations, A and B, and it has a body, which is the compound statement. So you can sort of see how the source code has been interpreted following a grammar, and we've built this logical representation, which can then be accessed and run and understood by a parser or some other program, which is built for these purposes. So what can we do with these abstract syntax trees? So once you have this logical representation of a tree, you can do basically anything to it. You can add more children to it in memory. You can basically modify. You can say, I read this source file in, but now in memory, I am changing the source code to look completely different. Like, you can do that. You can completely modify what a program looks like in memory. Typically, you don't do this because that would be a malicious compiler. That's not what you want. Otherwise, you compile A and get program B, which does nothing. That's not the same program. Well, you could make like a virus which does it, which would be pretty funny. But yes, so once you have this tree, you can modify your program in memory or traverse it. You can analyze it in any way because you now have this logical representation which you can play around with and poke, modify. So often things that you can do, you can look for certain properties in your program. You can say, well, I wrote. For example, if you're assessing someone's code, for example, if you're like for programming courses, you can have an exercise that says implement this function using only a single for loop, and then you can say, first of all, did they write the function in their code? Does that function even exist? And you can look at the tree, traverse it, look at all the function declarations, and say, yes, the function exists. Or you can look at, if they have the function, but have to implement it in the way which I want them to implement it. You can say, well, does it have a for loop, for example? Yes, you can look at the body of the function and look at its children and see, does the body of a function have the for loop? And does inside that for loop, do they do the particular things you expect? So you can do a lot of things with a tree. You can do a lot of static analysis of source code using these trees. And you can also do type checking. So often in the compilation process for most programs, it goes through many stages. So I think, for example, if you compile a C program, it goes from the source code, becomes an abstract syntax tree. That tree is then analyzed statically to type check all of your variables. And once type checking is finished, then it moves forward and then gets compiled into object code. There can be a few more stages depending on the compilation process, but you can do a lot of these sanity checks using the trees. Also, something that's pretty good that you can do with these trees is you can construct things called control flow graphs. So once you have the structure of your program in memory, you can then see how your program would run without running the program itself. You can just look through the nodes and see if it went through an if statement. If it's true, you'll go in here. If it's false, it'll go in here. So this is a control flow graph, and they're built using the abstract syntax tree. So when I said before, your program goes through several compilation steps. Typically, what would happen is you would have the source code, it becomes the tree. The tree then gets used to make a control flow graph. The control flow graph would then be analyzed to see to generate warnings. For example, it will look for unused variables, look for certain patterns in your program which are known to be errors, for example. And the control flow graph can be used to augment your tree. It adds more data into that tree for analysis purposes. And you can then use these graphs to do a very in-depth analysis of code to make sure that everything is working as expected, or it has a certain structure you want. And you can also take it a bit further to detect certain errors or even optimize your code. So because they control the logical flow of your program, you can then go through your program systematically and look for different aspects of it. Like you can say, hey, please check if whenever I access an array, for example, if this is in C or in Java, or any base array access, am I always memory safe? Because you can look at the size of an array you create, and then once you know the size, you can look at all the indices, all the variables you use as indices, and see are any of those variables greater than the size I created before. And you can do quite an in-depth analysis of array accesses and see, is my program memory safe with regards to arrays. You can also check if you have unused variables. You can go through your program step by step in the control flow graph and see, and then just create a set of the variables which have been modified. And if there's any variables which haven't been modified but haven't been used, you can then print out a list of unused variables. So you can do that. You can also look at if you've mallocked some memory. This is in C. When you've allocated a block of memory, you can keep track of the pointers and then see have you reassigned this pointer and not freed it before reassigning it, for example. And you can detect accesses to memory you've already freed, for example. A lot of research has been going into code optimization in the past few years. So with this control flow graph, you can go through your program and see, are there any expressions in your code which are duplicated? For example, like if you have A equals x plus y, B equals x plus y, well, you can optimize that to have the x plus y done once and just assigning the variables. So you can save a few program operations and then make your code more efficient in that way by looking at these sort of analyses. And I think one of the, if with compiler options, you can add like -O3, for example, to your C compilation step, and it does some loop optimizations for you, which can make your code a lot more efficient as well. It tries to look at how you access memory inside loops and how you're using your indices. It can combine loops together. It can modify those accesses to be more memory efficient, so it's cached more efficiently. You don't have many memory misses when you're accessing memory. And that's an ongoing research these days, is how to improve these optimizations and figure out the conditions under which you can make these optimizations safely without breaking how your program actually works. Because when you do these optimizations, you have to be careful that you don't break the actual operation of the code. Like it's good, like you can make any program run in constant time just deleting everything, but that's not really what you want. Unless, it makes for an interesting program just to do nothing, but it's very efficient. It's efficient at doing nothing. So so you want to have optimizations which don't modify how your program runs. Okay, so that's the basics I wanted to cover in terms of the initial steps of analysis of what abstract syntax trees are and control flow graphs. And now I'm going to go into the LLVM framework. So LLVM, it's basically this giant collection of tools and technologies which have been developed over the past few years which help with code. So it can be code debugging. I think they have the Clang compiler, which you most likely have heard of, so you can compile C programs, C++, and Objective-C. They have their own debugger, which you can use to debug programs. They have an implementation of the C++ specification. So they've implemented these libraries. So it's a whole collection of these tools which they have made, and all of those tools are under the hood of the LLVM project. So it's a giant project, but they have a lot of small tools inside of them, which are very useful for analysis and code-based operations. So how does LLVM actually do compilation? They do it in a bit of a different way than most compilers. They have a novel way of compiling, and this came out I think in 2002 was the paper I read on this. And this is, I stole this draft from that paper. So basically, LLVM, where your typical compilers would take your, takes your code, creates the syntax tree, and then just takes the syntax tree and turns it directly into machine code for the machine you're running on. That's the typical compilation process. And LLVM does it a little bit differently. So instead they have their own instruction sets that they use. They have their own intermediate representation of code, which is almost completely machine agnostic. So this representation language, it doesn't define anything to do with it doesn't define any machine dependent things. So it doesn't say, it doesn't give you I/O or memory management or signals, because that depends on machine basis, depending on what hardware you're running. So instead they compile your program into bytecode, but the bytecode it compiles into is LLVM bytecode. And then once your program gets linked, so in the linking step, that happens after compilation, then that bytecode gets converted into the correct machine instructions for the machine you're linking on. So you can have, so it allows the code you write with LLVM to be more portable than most compilers. There's still some machine dependence, but you're able to compile things on a different machine and then link them later on, which can be more efficient because of this bytecode representation. It then adapts to the machine you're running things on, or the machine you finally link the final executable on. And some of the bytecode as well gets embedded inside of the binary, and it allows LLVM to optimize things at runtime. So at runtime, they can make modifications and optimization to your code as it is running, which is pretty cool. So yeah, so it's an interesting way of compilation, and it's quite an interesting idea of how to make code that's more machine independent. You can run it on different places and still get the same result relatively well. And then the main thing we're going to look over today is the LibTooling framework. So it's one of the APIs that LLVM provides. It's a library which they've written to support writing standalone tools. So things that use the libraries and the compilation libraries of Clang and their compilers. So the Clang compiler, these libraries essentially tap into that compiler's code and APIs, and allows you to then take those things and run the analysis tools as though you were as though you were the compiler, as though you had access to those syntax trees and the data. So this library is written in C++. It's really, really well documented. I think this is one of the most well documented projects I've seen. So for example, they have examples of how to use their code, how to write tools. And so I'm basically going through a more in-depth version of their examples based on a tool I wrote about a year ago. And so they give very good explanations as to how to use their code, as well as the documentation of the functions and things in the library is also really well documented. For example, if I go and just look for LLVM, let's see what's AST matcher. I can let's look for something that's more. Let's see what's eyes. So you can see there are a lot of Doxygen documentation. So Doxygen is all of their tools, the entire library, and look for documentation if you're stuck or don't really know what a method does. You can easily look it up, and it goes through all the methods that tool has, as well as some of these also have examples at the bottom of these pages. But yes, it's a really, really well documented library. I would recommend looking into it. Very easy to understand as well and extend things. So yeah, so the main thing is it allows you to analyze the syntax trees of source files you provide the library, and it does this in a way that is quite easy to understand and create your own tools from. which is very good. And yep, so that's what we'll be doing today. So I'll put that on in case you guys want to need the link to that repository. Although if you guys start building it now, it might be a bit late before you guys can follow along. But yes, so demo time. So what I've done, so this is the code you would get from the repository. So what it's just a single file, and all this program does is it does command line argument for parsing for using the default things. So what it does, I've included the necessary libraries to use the LLVM tools. I created something called an option category. So it's like saying my program will be using these command line options. And I've added a basic help message to the command line arguments as well. So this is all a global state which gets modified. I've also added, as an example, a verbose flag to the command line options for the program. So to do that, I just made an option which returns a Boolean. It's going to be called verbose, so you do -- verbose on the command line. The description is generates verbose output. This init says what is the initial value that this flag will have, so the default is false. And then I'm adding this flag to my category which I created for this tool, which is UPCS demo options. This here is a warning consumer, so you can tap into the warnings, the compiler warnings that the tool generates when it parses the programs, the source files you give it as arguments. And many times when you want to write your own tool, in this case, I turned off the echoing of those warnings because they were superfluous in this case. There's a few warnings that are emitted by the Clang compiler just because it's a bit outdated on my machine. So I just turned off those warnings so I can show you guys the core of the analysis tool we're going to build. So this here just turns off the warnings. I've left some space here for what we're going to add later on. So the way this tool works is you create callbacks. So you register functions and classes which you want to run when you reach a certain point in the syntax tree. So what the tool does, so I've made an AST consumer, so that means an abstract syntax tree consumer. It consumes nodes in the abstract syntax tree. So whenever the tool runs through that tree one object at a time, it traverses that syntax tree for you. It passes that node, the thing it just went through, into this consumer, and this consumer then passes it off to any registered callback handlers which you want to do to handle those, to do any checks or analysis on. So you can pass off any nodes to some class which then analyzes that node and does certain checks. It'll become a bit clearer a bit later. Yeah, so this consumer just registers callbacks and provides so any of the things it finds, it passes on to any things you've registered. And this is the front end action. So the front end action is the key thing that the LibTooling framework provides. Is it allows you to run a tool or a set of actions via its tooling interface. So here, all it does, when it creates a consumer, it just creates the consumer that we want, which we've registered all our callbacks to. So it just gives the thing that gobbles up all the nodes and passes it off to the handlers. And then this is the main function. So all it does, it checks the command line arguments. So by default, the command line arguments expected by the option parser are a list of file names. It checks if you have, if you've given it the correct arguments. Once it's done that, it checks if you've given it any files. If you haven't given it any files, it says no, you need to give it some files. It then checks if you can access those files, because you can't really parse something you can't read. And finally, this is where the magic happens. You create a new tool with the compilation options. So this is known as a compilation database, which basically it says how each of the files got compiled or will be compiled. And you can specify this using an external file. But in this case, if you don't do anything, it just gets the default compilation database, which is empty. So it uses the default rules to compile each of those programs to generate those syntax trees. But you can specify a database file to do that. So what it does is you create a tool with the compilation database and the files you were given. Here I've just turned off the warnings by setting the diagnostic consumer to be the thing that does nothing. And then I just run it with a new UQCS demo front-end action. So this is where this front-end action will create this class here, and that class will be, and then the tool calls to create AST consumer on this action we provided to it. It then gives you the consumer, and the consumer has all of the registered callbacks, which will then do things on the nodes in the syntax tree. So yes, so that's the basic structure I've given you. So if I run it, so I've already built the tool. So the tool will be available under, is this big enough? Yep, can you guys read that? It's big enough. Awesome. Yep, so the setup script will download the LLVM project code into that directory for you. And then inside of that, under build bin, that's where the created program will be. If I want to build it again, I have to be under the build directory, and I can just use Ninja UQCS demo. So that's the name of the tool I've registered, and that's what the setup script does. And it'll try to build it. I built it beforehand because I know it takes a while. So I can just run it at the moment. So I would do /bin UQCS demo. I can now, if I do nothing, it just says there's no input files. If I give it a file, so I've provided a test file here, so it's check.c, which says some magic in it. If I pass that file to it, we'll see what it does. So if I do this, just back to my source, test files, and check.c, you can see it does nothing because I haven't registered any callbacks. It doesn't do anything at the moment. You can also use predefined front-end actions. So one of them is called the dump tokens action, for example. So this will create a action which all it does, it'll print out all of the tokens inside of the source files you provided it. So if I save that and rebuild it, so just Ninja UQCS demo, you can see it doesn't take too long to build now because it's already built all the dependencies. So what will happen now is when I run this, it should print out all of the tokens inside of the check.c file. So here, a token is what I've said before, it's part of the grammar for the language. So if we run that, you can see what it does. Goes through from left to right through the entire file, and it finds all of the tokens. So int, add, left parenthesis, integer a, comma, int identifier. You can see, so this is sort of what the tokenizer sees, and these tokens get combined to form the syntax tree itself, and then those objects get passed through. So yes, so you can see how these sort of actions work. In this case, the action we wanted to use is UQCS demo front-end action, which does nothing at the moment. So the thing we want to do today is let's make a program which will go through all of the function declarations inside of a C source file. So we want to look at all the functions like add and main, and just to see, do those functions, are they UQCS enough? Do they have the word UQ in their name? And if they don't, emit a warning saying, hey, this thing doesn't have enough UQCS for happiness. So the first thing we want to do is we want to create a class which we want to run our actions on. So how do we do this? We create something called a match callback. So what we do, I'll do it over here, so callback classes. So we want to make a new class first. So this is C++ code. So I'll call it UQCS func name check. It'll check for function names. It is a public class, and it extends something called a match callback. So in the LLVM libraries, the match callback classes have a run method which gets invoked for each node that gets traversed. So basically, it goes through the tree. For each of the things you've registered, calls the run method on that thing, which then does any actions you want it to do. So I'll say match finder, match callback, and autocomplete is a wonderful thing. One thing to keep in mind is, so VS Code has the C++ extension added in. It does take a few minutes to index all of LLVM's files, so you might not have the completion happening quite yet. Sometimes it can also be a bit laggy because there's just so many files to process. So we make a new match callback, and it'll override the run method of that class, because that's the method that we call whenever we have a result that's matched in the tree. So we make a new public method. So in C++, you have a public like that. So there's a public section and a private section in a class. So we want to override the run method. And this run method, what it takes is a match result, something that's been given back to us from the, it gives us a node in the abstract syntax tree. And that's given to us as a match result. So as a match finder, match result. And it gives us a reference to it, so that's the ampersand. It gives us a reference to a result. I'll just call this a result. And because this method is, this is a subclass of the match callback, we want to override this method. So we're using inheritance here, we override it. So this method, let's have a look. So what we want to do, so that's the first step. We create a class which has a run method. And nothing special in it yet. The next thing we want to do is we want to say what sort of things do we want our program to match in the tree, because at the moment nothing's been matched, nothing's been registered to be matched, so it just goes to the tree and discards everything for us. So what we're going to do, we want to use something called an AST matcher. So if we look at the matcher reference, so LLVM allows you to specify elements inside of the abstract syntax tree using its own language, called an AST matcher. An AST matcher, which is just abstract syntax tree matcher. You can, for example, if I wanted to, let's see, where is the example? There's a nice example. Yeah, so if I wanted to, if I had a return statement like this, the return 42, and I wanted to match that return statement, I can say add matcher. I want to match a return statement which has an argument which is an integer which equals 0. So you can nest you can specify what sort of things you want to match, and this goes quite. You can do quite a lot with this. So for example, let's have a look. If I wanted to, what's a good example? Yeah, so there's a lot of different ways to do this. So if, for example, I can match binary operators which are less than operators, which has a right-hand side, the right-hand side of the less than sign, which has a child which is a 0. Like you can nest these things. In our case, so all of the matchers you have are listed in this reference. In this case, we want to match function declarations. So we can look at, there's a function declaration matcher. So we go back to our code, and we want to register our callback. And I'm going to do this inside of our AST consumer. So we have our matcher. So the matcher just is the thing which contains all the things we register. And whenever, so handle translation here, it says whenever you get a new file and its syntax tree, match the syntax, run matches on the syntax tree for that file is what this translation unit means. So yeah, so in Clang, a translation unit is just a source file, pretty much. It's a unit which has been translated into an AST. So all it does, we have a matcher which matches each file, and over here we're going to register a matcher into our match finder. So to do that, what we do is we add a, so we do a matcher, we add a matcher, so we add matcher. What are we adding? So we're adding, so it takes two parameters. It says, what have I done? Yeah. So we're adding a matcher. What sort of thing are we matching is the first argument, and the second one is what class do we want to have the run method invoked for that match. So what are we matching? We're matching a function decal. So that's from the previous, from the reference. So just it's a function decal. We don't have any specific functions we might want to match. We just want to match all declarations. And we also want to add a binding to it so we can reference this declaration by name. So I call it func decal because it works. And what thing are we going to, what class are we going to use for this? Well, we're going to use a new UQCS front-end func name check. Sorry, we want to use that class. We want to use that class to match so whenever we match a function declaration, we'll be using the run method of the func name check class, which will be this run method. Does that sort of make sense? Yep. So we've added a new matcher, so we've registered something we want to match, and now we have our class, which just does nothing at the moment. So the next thing we want to do, let's do something interesting for this. So we shall go through our check. So the first thing we want to do is you want to extract out the node from the match result. We want to get that AST node out of it, and we can do this via the get node as. So the result has a method called, so if I do result dot nodes get node as, so that allows you to basically cast that result to a particular thing. And I want to get it as a Clang function declaration. So that's the class which represents a function declaration. And that's the thing that will be returned from the match result. And we want to get it from the func decal. So that just says from that match we registered before with the binding, we can use the binding name here to narrow down what thing we're matching. So this will, in our match result, it'll find the things that were matched by this particular matcher called func decal. And it returns a const pointer to it. Yep, so that gives us the node we're looking at. So we extract the thing we wanted to match from that. The next thing is this will return null if it didn't match anything. So I'm just going to put this in an if statement. So like this, just so if we do match something, then we go into the if statement and we actually do perform operations on it. So if we do have a node, what we want to do is just we're going to extract the location of it in the source file. So source manager is in the LLVM libraries, the source manager is what you use to get information about certain locations in the source code. So you have something called the source location, which says I am a position in the code, and to resolve that location, you need to use the source manager, which knows about the locations. So we get the source manager, and then we get the location of this node. So location is just, you can use the get source location, or just get location, the get location method. So that gives you the thing to resolve the location with and the location you're resolving. So at the moment, I'm just going to print out the location of what we found. So let's do this. One other thing we also want to do is check if the thing we've matched is actually in a file we provided to the program as a command line argument. For example, if your program includes other header files, for example, this will match those as well, which isn't always what you want. So what I'm going to do here is I'm going to say if source manager is written in main file, if that location isn't in one of the main files we provided, we'll just ignore it. We'll just ignore this node. And then what we're going to do is just retrieve some information about the node. So we're going to get the name of it. So the name of the function declaration. So what is the name of the function we matched? So we get node get name. So how I know what these functions are, so all these methods are also inside of the documentation I showed earlier. So if you ever get stuck looking for these things, you can just look at the Clang libraries and you can find the methods. So we get the name of the function, and then we also get the line number of the function. Get expansion. Sorry. To get the line number, so we get the name for the node, but to find its location, we have to ask the source manager about the location. So we get the expansion line number from the source location of that node. All we're going to do for now is just echo out. So in LLVM, LLVM outs is to send it out. We're just going to echo name on line number and a new line, just for a good measure. So that's all we're going to do for now. Just we've matched a function declaration and we just extracted its name and line number, and we're going to print that out. So if we rebuild the program, hopefully it compiles nicely. Probably not, because I missed something. I think I've missed a semicolon. Yes, I've missed a semicolon. As usual. Now, where have I missed the semicolon? Source manager. There. No? Not source manager? No, that's right. Where have I done it? Line 78. Yeah, this is why you never do live demos. I think, yeah, there's a semicolon at the end of a class. Yes. Yeah, never do live demos, they never end well. Let's see, have I done this right? No, I have not. I've missed another semicolon at some place. Of course. Yes, we've added the matcher, but yeah. Yep, there we go. All good. Yeah, so it also takes some time to build things after a while. So if we run that, we can see there's add on line 7 and main on line 12. So we found these two functions, add on line 7, main on line 12. So now what we're going to do, let's check if the name doesn't contain UQCS, then it's not good enough for us. We must emit the error. We cannot let this injustice go. So I'll make a new function. I'll just do this. So if what do I do for that? Yes. If name dot find UQCS is not equal to string plus. So if it can't find the substring UQCS, then we must do something. So then we will echo online that. We can also add the file name for this, so add which file this thing came from. So otherwise, we know if we have multiple source files, you want to see where it comes from. In this case, to get that, we ask the source manager again. So file name is source manager get file name for our location. So there's not enough UKCS for the function online that. In file name. And to make this a bit funnier, so just to show an example of how we use these flags, so what I can do is I can say, so the flag I've given there is a global variable, so this verbose is global, so and it gets set globally. So I can say if verbose verbose, have it yell things, which is always a good idea. Okay, so if it's verbose, we also print out verbose, and then if we can't find UKCS, we also say there's not enough UKCS for the function. And if we recompile that, hopefully I've done this correctly, and don't have it compiled nicely, we should see some nice things happening. Yes, so that failed miserably.
Put a UKCS in the function name.
Say again?
Put a UKCS in the function name and see what happens.
Yes, I think I might have done this the wrong way. UKCS, let's see. Unless I'm looking at the wrong function, the wrong file. Yes.
I think it's supposed to be equal instead of not equal.
Yes.
If statement.
You are correct. If it is, if I can't find it, it's a yes. Yeah. There we go. Yeah, logic is hard at this time of night. Let's see. Aha! There's not enough UKCS for those functions. And then if we go to the file, which one is it? It should be. It should be. Hopefully this one. No, I think I'm looking at the wrong one. Let's just vim that file. I'm not going to search through the tree in VS Code. Yeah, let's make this thing UKCSable. UQC. Oh my goodness. Why does this do it? Why? I didn't. Yep. Never do live demos is what I want to say. UKCS add and UQC. QCS. Yep. Eye contact. UQCS. Yep. Yes. Which is good. So it found the one, didn't find the other. And there you go. We've made a program which yelled at us if we don't have certain properties in our code. We can also for yelling, make it verbose, make it yell. If I can type verbose. Haha, verbose. It hates us. So yeah, so the very basic thing, you can add these matchers to, you can register them, have them look at certain nodes, and then have them perform actions on them. So this is a very basic program. So an example of where this, taking this to a whole, like to the extreme. For those of you who've taken CSSE 2310, the style checker, I wrote that to, and so the same libraries. So basically, if you look at its main file, it has a lot of checks. Same format. It has the command line arguments with a flag, one flag. Has the same diagnostic consumer. I did not copy this at all. But you can see here, instead of having like one matcher, you have a lot of different things you're looking for at one time. So you register a lot of matchers. Each of those things does certain checks on the syntax tree. You can also add preprocessor callbacks. I skipped that for a time. But yes, so you can do a lot of these checks, and you can actually get very complex programs and checks just using this basic framework, and it's very easy to extend as well. But yeah, so that is the end of the demo. Does anyone have any questions?
With the style checker, it would be checking white space and things like that, which are normally removed in an abstract syntax tree. So is that like an earlier step you can look into?
Right, yes. So in terms of, so the syntax tree here, so the style checker, I had to jump through a few hoops. So the thing with LLVM, their syntax tree has access, so with the source manager, you can query it for tokens and white space. You can ask for, give me information about that part of the source file I'm looking at. So what the style checker does is it scans through the white space part of it, or it looks at what column number am I at, and then does the arithmetic to see, am I further where I should be. So it keeps track of the indent level, so how many compound statements the thing's nested in. For each compound statement adds an indent level, as CSCs is this times indent level equal to the column number, for example. For like other white space checks, like seeing if pointers are the right way around, it does a manual scan through the source because you can look into the source code directly. But yeah, so the syntax tree does typically throw away the code, the source code at all, completely. In this case, LLVM is nice in that their libraries keep that intact for you, which is nice. Yeah. Any other questions? Yep, but that's all from my talk. Thank you for coming. Hope you guys enjoyed it.
Thank you very much, Dani. Let's see if I can get in the camera. All right, so there is your mug, complimentary. Pizza is almost here, so we'll be heading over to GP South. Don't forget, on Thursday we have online games night on the Discord. If you're not in the Discord already, I don't know what you're doing. discord.uqcs.org. And also Hackathon is also coming up with the postponed date of week 7, end of week 7. Tickets are on sale, hackathon.uqcs.org. And I think I've showed enough. Thanks for coming, everybody. Pizza should be here very soon.